Good morning, everyone. So, today in chemistry, we are going to discuss another subtopic from periodic table, that is F block elements and their general properties. F block elements. The first point about F block elements is that F block elements are the elements which are placed at the bottom of the periodic table, right? This is some rough idea of the periodic table, and here at the bottom of the periodic table we have two horizontal lines. So these two together are known as F block. Elements at the bottom of periodic table. Elements at the bottom of periodic table in two series are called F block elements. In F block elements we have two different series. One is known as lanthanide series and another one is known as actinide series. So in F block we have two series, right? One is lanthanide series and another one is actinide series. These are the two series in F block elements. Lanthanide series starts from lanthanide series lanthanide series starts from atomic number 58, that is Ce, and it goes to atomic number 71. This is lanthanide series. And actinide series starts from lanthanoids actinoid series. It starts from thorium Th, that is 92 Lr with atomic number 103. So in F block we have two series, one is lanthanoid series and one is actinoid series. Lanthanoid series starts from Ce 58 atomic number to 71 atomic number, and actinoids is from atomic number 90 to 103. Next point is all elements in F block are metals. Are metals. In F block, all the elements are metals. And they have extremely high melting point and boiling point. All the metals or all the elements in F block have extremely high melting point and boiling point. High melting point and boiling point. Understood? They show variable oxidation states. Variable oxidation states. And in these two series, actinoids are radioactive. Actinoids are radioactive. Actinoids are the elements in actinoid series, and lanthanoids are the elements in lanthanoid series. So when we are calling actinoids, it means we are talking about elements in actinoid series, and all the elements in actinoid series are uh, radioactive elements. And the next point is, what is the general electronic configuration of F block elements? So general electronic configuration of F block elements, and it is given by n minus 2 F 1 to 14, n minus 1 D 0 to 1 or 2, and ns2. This is the general electronic configuration of F block elements, right? So these are the general basic properties of F block elements. The main point is that there are two series in F block elements, lanthanoid series and actinoid series. One more point in it, that elements after uranium are called or are known as transuranium elements. This is very important point, that elements after uranium are called transuranium elements. Next topic in this chapter, we have trends in periodic table. Right, in the last two sessions we have covered general properties of block elements. We have discussed some properties of S block elements, some basic properties of P block elements, and some basic properties of D block elements, and now there are some basic properties of F block elements. In all these sessions we have also discussed about the position of elements in periodic table, right? And now we are going to discuss a new topic that is far more important in periodic table, and it will be used in complete inorganic chemistry. There will be widely use of these trends in periodic table in groups and periods. So this is very important topic. The topic is trends in periodic table. Trends in periodic table. Now, before studying the trends in periodic table, we have to be familiar with some basic terms or terminology which we are going to use in periodic table. Trends in periodic table. So, first of all, we will define some basic terminology or terms. Then we will use how the trend is in periodic table. And the basic terms which we are be using here are atomic size, or sometimes we call it as atomic radius. Second, we have Z effective, that is effective nuclear charge. Then we will have uh, ionization enthalpy. Then we have electron gain enthalpy. Electronegativity, electronegativity, and metallic nature, metallic and non-metallic nature. What do we mean by metallic nature and what do we mean by non-metallic nature? Then sometimes we use here oxidizing and reducing nature. Oxidizing and reducing nature. Then in periodic table, sometimes we use about acidic and basic nature of acidic and basic nature of oxides of the elements. These all are the basic terminology which we are going to use in this topic, trends in periodic table. So we will start from atomic size or atomic radius. Let me check once if there is something left. Electron gain enthalpy is done, electron negativity is done, oxidation state, yes, done. So now we can start from atomic radius. Atomic radius or atomic size also referred to for the same concept. What is atomic radius? Let's say we have an atom of any element, and this is nucleus, and this will be the outermost cell. This is what we are calling a nucleus, and this is our outermost cell. So atomic radius is defined as the distance between central part of the atom to the outermost cell, or the distance between the central point of the nucleus to the outermost cell. That is known as atomic radius. So we define atomic radius as distance between center of the nucleus and outermost cell of the atom. That is known as atomic radius. Second point about atomic radius is that we will we will have it in angstroms or picometer. Basically, we will use picometer for it. So unit for atomic radius is picometer. 1 picometer is equals to 10 raised to power minus 12 meter. This is 1 picometer. Understood? In atomic radius or atomic size, we have some different concepts for different elements to define the size of the atom or the atomic radius. Basically, what we have written here, distance between center of the nucleus and outermost cell, this is not a very precise definition for the atomic size or atomic radius. There are different elements which lie in different way. The the arrangement in which elements exist is different for different elements. So the atomic radius or the atomic size of different arrangements will be different. And here we will have some basic idea about that. So in atomic radius, one of the point which we discuss is ionic radius. Ionic radius. What is ionic radius? This the concept will be same. And ionic radius will be defined for ions, right? It is defined for ions. And in chemistry, we have two categories of ions, right? One is positive ions, another one is negative ions. Positive ions are known as cations, and negative ions are known as anions, right? So, how a cation is formed? A cation is formed if we have an element and the element loses its electron. Let's say it loses an electron. So if any element will lose an electron, it will have plus n positive charge. So if any element is with positive charge, then we call it as cathode. We call it as cations, or the ion with positive charge. And on the other side, how an ion is formed? In this case, element will accept some electrons. Let's say it accepts an electron, and we will have E with minus n charge. Then we call it as anion, right? So if we are having a positive charge, then the atomic radius of positive ion will be ionic radius, right? For example, let's say we have sodium atom, and sodium atom loses its one electron and it becomes Na plus. On the other side, we have chlorine Cl, and it accepts one electron and becomes Cl minus. Now we will try to understand how the radius or the size of the atom is changed by losing one electron or by gaining one electron. Basically, we want to check how the size is changing after gaining or losing electrons, right? For that, we will check what is the size of sodium atom. So if I will write here for condition for sodium atom, condition for sodium atom. So we have sodium atom as sodium with atomic number 11, and its arrangement of electronic configuration or electronic arrangement is 2 comma 8 comma 1, right? And if I will write here for sodium Na plus, what will be the arrangement of sodium Na plus? If we will go by a chemical reaction, let me write it in this way. Here we have arrangement 2 comma 8 comma 1, right? And one electron is gone from sodium atom, and it is now Na plus. So now if you will look at the electronic configuration, you will notice that electronic configuration of sodium is 281, and there is one electron in the outermost cell. So if we will try to lose one electron from the sodium, or sodium try to lose its electron, it will lose its outermost electron, right? Sodium cannot lose its inner cell electrons, like it cannot lose one electron from second cell, it cannot lose one electron from first cell, it will always lose its electron from the outermost cell. So if I will draw here the cells, it will look like this, right? This is the arrangement for sodium, and here we have 2 electrons, here we have 8 electrons, and here we have 1 electron, right? And if it loses its one electron, what will happen? The outermost cell will be gone, because there is only one electron in the outermost cell. So if one electron is gone, then the outermost cell will also be gone. There will be no outermost cell in sodium ion Na plus. So Na plus will have electronic configuration like 2 comma 8. It was 2 comma 8 comma 1 before losing the electron, but after losing the electron it is 2 comma 8, which indicates that before losing electron there were 3 cells: K cell, L cell, and M cell. But after losing electron, there are only 2 cells: K cell and L cell. So M cell is gone, which clearly implies that the arrangement of sodium ion will be something like this. The third cell will be gone. So by this discussion, we can clearly state that if any element is losing electrons, then its atomic size will decrease or increase. Will decrease. Its atomic size or its atomic radius will decrease. So here we are having Na plus ion, and the radius of Na plus ion, if you will look at the from center to the outermost cell, then this will be ionic radius. This will be what? ionic radius. And here if you will look at from here to here, this will be atomic radius. Understood? This will be atomic radius, this will be ionic radius. So the most important point here is that uh, positive ion, let me write it as positive ions are always smaller in size as compared to their father atoms, right? The size of positive ion is always less than size of the father atoms, right? Understood? So if I write here Na plus and Na, if I write here Mg plus plus and Mg, if I write here Al plus 3 and Al, so we can clearly state that Na will be greater in size than Na plus. Similarly, Mg will be greater in size than Mg plus plus, and aluminium will be greater in size than aluminium plus 3. So in general, we can write here that E plus N is always less than E, right? This is the general trend for size in atomic. This is the general trend in ionic radius, right? So if we want to define ionic radius, how will we define ionic radius for ions? We can write here that ionic radius is the distance between ionic radius is the distance between ionic radius is the distance between center of nucleus to center of nucleus and outermost cell of the ions. Whether it is positive ion or it is negative ion, doesn't matter. The definition will be same. Next, we will look on how the chlorine is 1 electron. So this time it is about chlorine. If we will look at the chlorine, it is 2, 8, 7. So there are 3 cells in chlorine atom, K cell, L cell and M cell. Now let's say chlorine accepts 1 electron. If chlorine accepts 1 electron, it will become what? It will become Cl minus, and the arrangement of electrons will be 2, 8, 8. That is electronic configuration will be 2, 8, 8. In this case, before gaining the electron, there are 3 cells. And after gaining the electron, again there are 3 cells, right? So is it the condition that atomic size of chlorine atom is not changing in this case? Or the size of chlorine atom will change? Means size of chlorine atom and size of chloride ion, that is Cl minus and Cl, will be different or it will be same? Let's have a look on it, how the size will change, if it is changing, and if it's not changing, then why will it not change? So for that, again I will plot, I will have figure for atom like this. This is nucleus, and then we have 3 cells, right? There are 3 cells, and electronic arrangement is 2, 8, 7. Now it gains 1 electron, and number of cells still are same. We are having K cell, L cell and M cell. But before gaining the electron, if you will notice, the nucleus of chlorine was trying to hold 7 electrons. right? And after gaining one electron, the nucleus of chloride will try to hold 8 electrons, right? So before gaining of electrons, it was interaction between one it was interaction between nucleus and 7 electrons. Now it is interaction between nucleus and 8 electrons after gaining the electron. So it will be somewhat difficult for nucleus to hold so much electrons, like one electron is extra now. So it will be somewhat problematic for nucleus of chloride ion or the nucleus of chlorine to hold on 8 electrons. So due to that reason, because we are gaining one extra electron, there will be little bit variation in the atomic size, because now nucleus is not very much capable to hold 8 electrons. So there will be less interaction between 8 electrons and the nucleus, and due to which there will be some increment in the size of the ion, right? Because before gaining of electrons, it is attracting 7 electrons, it is trying to hold 7 electrons, and now it has to hold on 8 electrons. So it will be somewhat difficult for nucleus atom, and that's why there will be some increment in the atomic size of the chloride ion. So it will be something like this, right? So we can state that after gaining the electron, the arrangement is 2 comma 8 comma 8, 2 comma 8 comma 8. But in this case, nucleus are attracting 7 electrons. Nucleus of chlorine is holding 7 electrons. But in the latter case, nucleus of chlorine is holding 8 electrons. So it will be somewhat difficult for nucleus of chlorine to hold on 8 electrons, and hence there will be some increment in the size of the chloride ion. So this is chlorine atom, and this is chloride ion Cl minus. So here we can say that the size of the negative ion, that is anion, will be greater than the father atoms. It will always be greater. So we can write here that size of negative ion, that is anion, is greater than size of father atom. Understood? So if I write here Cl minus and Cl, Br minus and Br, O minus minus and O, right? So what will be the size of Cl minus and Cl? So size of Cl minus will be greater than size of Cl. Size of Br minus will be greater than size of Br. And size of O minus minus will be greater than size of O. So here the general trending is that an ion with minus and negative charge will have greater size than its father atom. Understood? So this will be the arrangement. This was the discussion about ionic radius or ionic size. And here we have discussed about positive ions and negative ions, right? Okay, so the next point in the same subtopic which we are dealing with, that is atomic radius. We have discussed only ionic radius, right? Now we will look at a different concept, that is covalent radius. Next point is we define covalent radius for molecules which are covalently bonded, right? To define the size of molecules, we can use the concept of covalent radius, and this concept will be valid only for covalent bonded molecules or covalent bonded compounds. So this will be defined for covalent molecules, right? For example, let's say we have hydrogen H2, hydrogen H2. So hydrogen H2 is H bond H. It is covalent bonded. And the arrangement for hydrogen H2 is given by this Lewis dot structure. One of the hydrogen atom is here, one of the hydrogen atom is here, and there will be a sharing of one electrons, one electron from both hydrogen atoms. So this will be hydrogen molecule H2. And now I want to define what is the covalent radius of hydrogen here in this case, that radius of the hydrogen atom. So if hydrogen atom exists alone, if there is no bonding with hydrogen atom, then we can discuss the size of hydrogen at atomic radius of hydrogen. But in this case, hydrogen is bonded with another hydrogen, so it is covalent bonded molecule. And in covalent bonded molecule, we want to discuss the radius of hydrogen atom, and in this case we are calling it as covalent radius. Are you getting it? Covalent radius is defined for covalent molecules. Understood? So what is the definition for covalent radius? Covalent radius is defined as the half of bond length, half of bond length, or we can define it as covalent radius is the half of distance between the center of the nucleus of these two atoms. So R covalent is defined as the half of distance between center of the nucleus of two atoms in covalent bond. Understood? For example, if I will take the example of hydrogen molecule, it will be like this. This is one hydrogen and this is another hydrogen. Here we have the nucleus of first hydrogen and here we have the nucleus of second hydrogen. So the distance between them is this one. This is the distance d between nucleus, distance between nucleus, and half of this distance will be somewhere here, right? This will be the half, and this distance is what we are calling as covalent radius. Here it will be this one, covalent radius. This is first hydrogen, this is second hydrogen. So we can write as R covalent is equals to D divided by 2. And what is D? D is the distance between the center of the nucleus of two atoms which are covalently bonded, right? It will also be true for any two atoms. Like we are having A atom and we are having B atom. This is A atom and this is B atom. Nucleus of A atom, nucleus of B atom. So the distance between the nucleus will be this one, and its half will be like this. And this will be the covalent radius for atom A, Ra, and this will be the covalent radius of atom B. Understood? And total distance in this case will be Ra plus Rb. Understood? So R covalent will be given as D by 2, that is RA plus RB by 2. Understood? And unit for these radius will always be picometer. We will measure them in picometers. Understood? Okay, so next point is after covalent radius we have next van der Waals radius. So one more topic is van der Waals radius. Van der Waals radius is defined for van der Waals radius is defined for non-polar molecules. It will be defined for molecules which do not have dipole interactions. Or let's say we are having two different molecules which are interacting with each other, whatever may be the interaction, whether it is with dipole moment or it is not with dipole moment, whatever be the interaction, but two molecules are interacting with each other. If there are two molecules interacting with each other, then we can define this concept, or we define this concept for that case, that is van der Waals radius. How we define it? Let's say we are having two different molecules, A2 molecule and B2 molecule. So it is defined for interaction between two molecules, like molecules of chlorine gas, molecules of argon gas, molecules of hydrogen gas. In that case, we define van der Waals radius. And how it works? Let's say I have a molecule A. Sorry, I have a molecule A2. This is A1 and this is A2. So this is A2, overall A2 molecule. And here we have B2. This is A2 and this is B2. And these two molecules are interacting with each other. These two molecules are interacting with each other. So the distance between these two atoms, let's say this distance is D. And if you will do half of this distance, you will get van der Waals radius, because both the molecules will have some interacting region. There will be some interaction between them. So this distance between their centers is D, and R van der Waals will be D